pinned methods and want them to be robust across variant diffusion coefficient and especially for long time intervals. And we want them to be parallelizable in space and in time. The other thing I want to consider is the solution quality, and that is why, in convection diffusion problems, we have sometimes convection-dominated regimes, and there it is quite known that standard Galerkin methods suffer from non-physical oscillations. Therefore, we have a tool which is stabilization techniques to improve the numerical solution, and that is what we will look at first. So the model problem and the discretization and stabilization of the problem. Then we go to parallel in time methods, especially multigrid methods, which we already saw today. But space-time multigrid and multigrid waveform relaxation. And after that, we will look at somehow a combined approach. Okay, so this is the d-dimensional convection diffusion problem. We want to find solution U. We have the time derivative here and a right-hand side, some boundary conditions and an initial guess. We have the spatial domain as well as the time interval. And then there are some different effects. So the first one is the diffusion with a diffusion coefficient epsilon. This more or less smooth our solution. The second effect is the convection, where we have the velocity field V, and this causes the transport of the solution. So the combined effect transports and smooths, and we can capture these two effects by the Pickley number over here. Okay, so as a test problem, we do it in 1D, and we simply take as the velocity field our solution U, which is more or less the Burgers equation, so linearized version of it. And we have a manufactured solution that looks like this. We have a parameter eta, which we can vary, so it makes the solution steeper or smoother. So this is has a quite steep gradient here, and if we reduce it, it can look like this. So this is the test configuration that we use for our numerical tests. And we have a source term f that we compute so that the solution always looks like this. And in fact, it's at timestamp 0 that, in black here, and then we transport to the right. So my institute is into Navier-Stokes equations, and therefore this is more or less a sub-problem. So we need a solver to solve Navier-Stokes equations. Okay, so now we vary the diffusion coefficient. So this is a quite large one. Our Pickley number is less than 1. We see already the Galerkin solution here in green, and it fits our exact solution. If we now decrease the diffusion parameter here, we see some little oscillations already. But if we decrease it more, it looks like this, and the Pickley number is locally much greater than 1. So for this purpose, we want to use stabilization in order to improve our solution. This is the problem. We use Galerkin finite elements at this point, and have the semi-discrete variational problem here. And the stabilization we use is a variational multi-scale stabilization. So this means that we add a diffusive part and remove an anti-diffusive part, where GH is defined as the discrete L2 projection of the gradient, so that we ensure that the stabilization term vanishes in the continuous setting. So this is consistent, and also it's a higher order stabilization. So that's what we want. For quite simple test case, so linear finite elements, a uniform mesh, quadrature-based mass lumping, and fixed velocity field, we can write down the semi-discrete formulation in matrix form here. So M is our mass matrix. It corresponds to a scaled identity matrix. Then we have the diffusive part here, convective part here. And for our stabilization matrix W, we get L again, so already known from the diffusive part. And we get another matrix here. Because we use quadrature-based mass lumping, we can now multiply by the inverse of the mass matrix, and we get, come to finite differences. And in this context, we see, okay, these two here can be more written like this. And this looks quite familiar because it's the second order central difference quotient of the second derivative. And here, just with a larger steps mesh size, which is 2h. So we can also write down the Taylor expansion here. And if we now compute our stabilization matrix, we see this is a pentadiagonal matrix, which basically corresponds to a scaled biharmonic operator. And we are of second order of accuracy. Coming back to our test case, we now apply the stabilization to our solution, and we see that, the oscillations are smoothed. We use a stabilization parameter 0.1 here and level 5. If we refine the level, then we see, okay, the oscillations are also not there in the Galerkin discretization, but in fact, the stabilization also looks good. So we have two options to choose our parameter alpha here. So, the easiest one would be to choose it just fixed. That would be 0.1. And another option would be to be dependent on space and on time. So in fact, we choose it like this. It looks more or less, or it has the profile like the exact solution, and we couple it with the Piclet number so that we add more stabilization if we are convection dominated and less stabilization, over here. If we look at the error, we can even be better with stabilization, but if we have a fine resolution, then we are a little here, but we assume that this is okay. Okay, so I haven't talked about time discretization yet, so we will come to hint methods. We use the implicit theta scheme so that we have a linear one-step method. We have the implicit part and matrix A and an explicit part and right-hand side here. A special characteristic that we studied is to treat the stabilization term fully implicit. This was especially considered for Craig-Nicholson's scheme. And as we saw, the stabilization matrix has a larger bandwidth. So if we only edit here, maybe we reduce a little bit the computational effort. And moreover, there's no loss of accuracy, so still got second order here, and it was very effective regarding the solver. From this sequential formulation here, we now block our unknowns in one vector, but in two different ways. So this way is quite common. We already saw it. So we go to the first time step, take all unknowns, all spatial unknowns, then go to the second one, and so on, and that would result in this vector. So if we do it in another ordering, where we first look at the first spatial node, and all time steps, then go to the second. This is, we like to call it the space major ordering. And matrices then, the system matrices then results in these structures. So for the time major ordering, we have this overlying structure from our time discretization. So we have a lower bidiagonal matrix here, and if we have no stabilization, then we have, and in 1D we have this tridiagonal structure from our spatial discretization as block in those blocks. On the other side, this is just transformed. So we have this overlaying block tridiagonal structure from our spatial discretization, and we have all spatial nodes over here. So the blocks are not of the same size, but the general system has the same dimensions. If we now use the block diagonal as a preconditioner for smoother and multigrid methods, then this basically leads to two different methods. So one is the space-time multigrid. The other one is multigrid waveform relaxation, which is motivated in a different way. So the first one, was introduced by Ganda and Neumüller, and we can parallelize in time, but also in space. So we have a multigrid in time here. We can additionally solve or approximate our preconditioner D with another multigrid in space. Therefore, us can parallelize in space and time. And one says we solve a full space-time problem here. So if we only do coarsening in time per spatial node, then we get a V-cycle like this. So on the fine level, we have a time step size delta t, then we double it on the coarser level. On the other hand, multigrid waveform relaxation was introduced by Lübich and Ostermann, and it is not parallel in time, but enhances parallelization in space. So one can interpret this system as a space-only system, but with vector-valued nodes for each spatial point. So this, we like to call it time simultaneously. And here we only like to coarsen in space, but for each time step. So prolongation and restriction operators are both Kronecker products. And here you see the V-cycle in this case. So first numerical studies without stabilization for diffusion coefficient epsilon to the power of -2 for this time multigrid. We have the number of iterations here, and we look at some different time steps, number of time steps, and we see, okay, this is, we get really low number of iterations, and this looks really good also for multigrid waveform relaxation. One difference here, we use the FGMRES, so the flexible GMRES, because we have another multigrid in space inside of the multigrid, and there we use the GMRES smoother again, and therefore the preconditioner changes. So we need flexible GMRES here, and here we just simply use the GMRES as well. We now reduce our diffusion coefficient. We see that these methods have some problems. So coming back to the stabilization, we already talked about our stabilization parameter, and we studied it especially for the multigrid waveform relaxation, so where we coarsen in space. So in fact, we decided to reduce the stabilization parameter on each level by a factor of 4, which is due to the fact that we want to solve the same continuous problem on each level. And as we saw, we get this capital H if we are on a causal level as the factor in front of the fourth derivative, and if we multiply with this vector, this cancels out so that we ensure we solve the same continuous problem here. Yeah, these are results for applying this stabilization for multigrid waveform relaxation. One is the fixed stabilization parameter, the other one, the one that depends on space and time. And we see, okay, it is a bit better than before, but yeah, we are in a limit. Like maybe we can block up to 100 time steps here, but after that, the number of iterations start rising. We also tried it out for space-time multigrid, and this looks, yeah, better, I would say. Yeah, I mean, this was an experiment, so we also wanted to do coarsening in space and time, and as we already heard today, this has some problems again. So, okay. Yeah, so now both methods offer powerful tools, but if we go to low diffusion or large time intervals, we have problems, and the number of the number of iterations should be low and bounded. So that would be really nice. So now an idea is to apply a geometric multigrid in time and couple it with multigrid waveform relaxation as an inner block smoother. So this enhances space parallelism, but also we can be parallel in time due to a splitting of a time interval. I will show this in a second. Moreover, we want to do both coarsening in space and time so that we ensure small coarse-grid problems here. So smoothing then would look like this. We have a time interval here and do a splitting like this. So we have two time intervals, and then the system matrix would be split at this point. So if we apply Richardson iteration, then our preconditioner is are the red blocks, and we compute the residual. Then we split the time interval into I subinterval, and these subproblems should now be solved from our multigrid waveform relaxation, and up to a tolerance of 10 to the power of -1. And after that, we do the correction step. Then about coarsening, we have a fixed number of subintervals, which is 4 in this case. And if we coarsen, we have a larger time step size. So we want the number of time steps per interval to be reduced. This is not that bad because then our processors correspond to fixed subintervals that may reduce communication costs. But this also limits the number of levels we can have. So in our numerical studies, we say we want on the fine level to have 32 time steps in one subinterval. And for this case, we saw that the computing time was only under 1% for the coarse-grid solver. So assume this would be okay. And also a note, if we would do it in another way, so fix the number of time steps to 1 per interval, then this would lead again to space-time multigrid. Okay, so results for quite large diffusion parameter. And these are one of the multigrid in time. These are the one of the inner multigrid waveform relaxation, and we use the V cycle here. and for now do only coarsening in time. So these are quite low. That looks really good for different time step sizes and hash sizes. And then we reduce the diffusion parameter coefficient again, and you see, okay, it starts rising a bit, but it's somehow still low. So we have, even if we treat more time steps here, then yeah, it could still work. And if we go back to our worst case, then we see this, but we don't forget about stabilization. So if we add our stabilization, and these are results for coarsening in space and in time, we see that our inner multigrid can work. So, and also the outer iterations are quite low here. Yeah, this is the last thing, some errors. So where we compare the error with stabilization and without stabilization, the discrete and true error at a final time. And this is just to show that, yeah, the error doesn't really rise that much, or yeah, it's even lower than in the stabilized case. Okay. So we saw stabilization can improve the solution, but also the solver. So if you apply it to a case where the solution looks good, this can still improve the solver. And our combined methods, yeah, works at least somehow. And some more aspects are extensions to 2D and 3D problems, of course, and studies on computational and parallel efficiency. So this would be something we could do in 2D and 3D bit better. Yeah, on the right side, we did a cost ratio estimation where we compared the cost of the sequential solver with our combined multigrid solver. And yeah, this would look like this or like this. And these are some references. So that's it. And I thank you for your attention.
We're going for a few questions.